Hello, 2.6, here we go. Exponential equations that require logarithms to solve. And in 2.2, we already did exponential equations, okay? So these are exponential equations that you have to use logarithms with. And what I want to do before that is just review. This is a review here from these. This is what we did in 2.2. Okay, so review from 2.2. So we had equations like this, right? Exponential form here. And what was our goal? Our goal was to get the base the same, right? And that's still our goal here with all exponential equations. We're going to look at what happens in a different way. But here we want to get the base the same. I have 1 over 64. I have 4. So I'm pretty sure I can change these into each other. We talked in that 2.2 video that I have this fraction 1 divided by 64. I want to move this up. When that happens, this exponent of 1, right, becomes 64 to the negative 1 power, and all that's raised still to this negative a equals 4 squared. Okay, right, so the 1 becomes negative when I move it up. And I want to get the base the same. I have 64, 4. Well, we've been doing these for a little while. I'm pretty sure 4 cubed is 64. 4 times 4 is 16. 16 times 4 is 64. So this is 4 cubed. So I'm going to change that into 4 cubed. So I have 4 cubed, but there's also this negative 1. So I'm going to change it to a negative 3 because those multiply. And they're still multiplied by negative a here, right? Equals 4 squared. And now they have the same base. I have 4 and 4, and so I can equal these exponents. So negative 3a times negative a is 3a equals 2, right? Because they have the same base, so I can equal, divide by 3, and there's my value, 2/3. Right? So we've done those before. That was in 2.2. We should know how to do those. So these are ones that we're going to require logarithms. Okay? So what happens when you cannot change one base into the other? When this happens, like in the last example, we just changed the bases into both being 4. But what happens if you can't do that? Like look at this example here. We have 15 and 96. Can I change those into each other? No. 15 squared is already 225. And there's nothing smaller that 15 can, I guess, break down into with exponents. And so I can't use exponential equations. So when that happens, I need to use or add either the natural log, which is ln, or the common log, which is log, right, or just log, to both sides, and then use the LOLs to solve. Okay? It's important here that it says to both sides. I can't do something to just one side of an equation. I have to do it to both. Okay? So, solve each equation. Same idea as the last one, except here I can't change this base into the other. And so what I have to do is either use log or ln. It doesn't matter which one you use. My guess is most of you are going to use log, but I'm going to show you one where you have to use ln. But, so I have log here. I'm going to add it to both sides. So I have log of 15 to the x power equals log of 96. And again, I could have used ln. But since I added this to both sides, that's okay, right? The equation's still equal because I added the same thing to both sides. Now use LOLs. Remember we had those 3 LOLs. The first one was adding, second one was subtracting, the third one was about exponents. And you'll notice here that I have an exponent. So this is why we do this. So once I put this log in front, this exponent can come down here. Okay? And so that makes this x times log of 15 equals log of 96. And that's because of LOL 3. Right? An exponent comes down to be a coefficient. Well, I want to solve for x, so now I have x here. I want to get it by itself. This is multiplied, so I'm just going to divide here by log 15. Okay, and once I divide these, that should get me my answer for x. So I'm going to go back here and use my calculator. Log 96 divided by log of 15. Okay, so log of 96 divided by log, what did I say, 15? Okay, and that's my value for x. Okay, it says to round to the thousandth, 10,000th. So hundredths, or tenths, hundredths, thousandths, 10,000. So this means to 4 decimal places. So looking here to 4 decimal places, 1.6854, but this 7 rounds this 4 up, right? So 1.6855 is going to be my answer. Okay? And so it's that same process. The idea, though, just to point out, we couldn't do this until we got this base and exponent by itself, okay? And so that's going to be the key in the next 2 problems that we do. We got to get these base and exponents by itself. All right, let's roll some dice here. Here we go. Add that sum up. Put that in the CPP. All right, the next 2, same idea. You'll notice they're a little longer. Okay, so what I just said is important. We need to get that base and the exponent by itself. So in number 3 here, you'll notice I have the e. Okay, and I did this on purpose. When you see an e, I'm going to tell you it's going to be substantially easier to use ln instead of log. In that last example, we used log, but you can use either. I'm going to use ln because ln has a base of e, right? But before I do anything, I need to get the base, which is e, and the exponent by itself. And so what's on the same side as that? Well, this 8, right? And this is 8 times this. So I want to get rid of that. I'm going to do that by dividing. I'm going to divide both sides by 8. Okay? So 81.2 divided by 8 is 10.15. So e to the 4.7a equals 10.15. Okay? So now my 2 bases are e and 10.15. Well, I definitely can't change those into each other. So in order to solve, I'm going to add an ln to both sides, right? That's what we just talked about in this last side. Add ln to both sides and use the LOLs to solve. So I'm going to add an ln here and an ln here. Now I have ln of e to the 4.7a equals ln of 10.15. Okay, the reason we do that is because we want to solve for a, right? And so now, once we add in the logs to both sides, this 4.7a comes down. And so I have 4.7a times ln of e equals ln of 10.15. And so, same idea, I want to get this a term now by itself. But I see something I can eliminate. ln, okay, ln, right, is the same thing as a log base e. We talked about that in the, what was that, 2.3? 2.3. So ln e is log base e of e. When we talked about this is one of the properties I put next to the LOLs. But this, right, we can evaluate equal to x, log on one side, so I can evaluate by changing it into exponential. So e to the x power equals this e. And so this is e to the first, right? So x equals 1, right? Here. And so this ln of e, basically, the reason that I used ln here is so that I know that this ln of e can cancel out to be a 1. And so I don't really even need to put it anymore because times 1 is by itself. So this turns into 4.7a equals ln of 10.15. Because that ln of e, here we simplified it to be 1. Okay. Now to get the a by itself, divide by 4.7. And that should get me my a. So ln of 10.15 divided by 4.7. ln of 10.15 divided by, close that, divided by, oh my gosh, I'm being forgetful. 4.7. Okay? And here I get my answer. And again, to the 10,000, so 4 decimal places, so 0.4930, but this 7 rounds it up, so 0.4931 is going to be my answer. Okay? So when I have that E there, I'm going to always use ln. And you can use it on other ones too, but definitely on that one. All right, number 4 is a little trickier. Doing one of these so you can see them. Again, bases, I can't change them into each other, but I want to get my base term and my exponent term by itself. So here, that term is this, 19 to the x minus 7. I want to get this by itself. Now I covered up that multiplication. So, to get that by itself, treat it like a variable. First thing I'm going to do is subtract this 4 to the other side. Okay? Now I have negative 3.7 times 19 to the x minus 7 equals, this is negative 70. Okay? Again, I'm trying to get this term by itself. This is multiplied, so I'm going to divide by the negative 3.7. So 19 to the x minus 7 equals, whatever this is, negative 70 divided by negative 3.7. Where's the negative on here? Okay. I should have planned for that. Alright, let's use this one. Okay, negative, oh my gosh. Okay, 70 negative? Okay, Miss Schulte. Divided by 3.7 negative equals, okay. So I'm going to round into the 10,000 just to try to get this as accurate as possible. So 18.9189. Okay? So same idea here. The reason that we do this, we can't change this base into the other. And so the reason we do this is to get this exponent down. So I'm going to add logs to both sides. I'm going to take a little shortcut here. Alright, and when that happens, this x minus 7 is the exponent, and so that's going to come down, right? And it's this is a binomial, so I'm going to put it in parentheses so I make sure that I remember it's together. Log of 19 equals log of 18.9189. So again, my goal is to get this x by itself. So I have this multiplication. I don't want to add this 7 over yet because I still have this multiplication. I could distribute this in, but that's going to make this problem a lot longer. So I'm going to go ahead. I have this multiplication. I'm just going to divide by this log of 19 first. Okay, so these cancel to be a 1, and now I'm left with x minus 7 equals, so we're going to have to do this on our calculator. So let's see if I can remember this one. Log of 18.9189, log of 18.9189, divided by log of 19? Yeah. Log of 19. Nope, don't stop on me now. Oh my gosh. Alright, so this comes out to me 0.9985. Again, I'm just going to round to the 10,000. So 0.9989. 9985. Okay, but I still want to solve for this x here. So this simplified to be this. So to solve for x, I still have to add this 7 over. And so this is going to be x equals 7.9985. Decimal should be down here. And you're welcome to do that on your calculator, but really it's just adding 7 to this number, right? So you should just get 7.9985. Alright, and that's it for 2.6. So we will see you in class. Bye.